So in the first example is before we start taking a derivative of this function, f of x is equal to x squared, let's talk about a couple of things that have been introduced in this section. So first, you notice that we have a new symbol. We have f and an apostrophe. And what that states is that we are taking the derivative of the function, and how we say that is f prime of the input x. So prime is just that little apostrophe or quote, whatever you want to call it. I forget what it's called, but essentially we're just taking f prime of x, which means let's find the derivative of that function. There is another way that we will learn that you can say this, which is the derivative d with respect to x. And I'm sure we're going to get into this where they're going to talk about taking the first derivative and taking the second derivative, which would be adding another little apostrophe there, and then on and on and on. So you can take more than just one derivative. Don't worry about that. We'll get into it later. I just want to let you know what that little symbol is, what it represents. So the next thing that we need to look at is this equation. I prefer to use this setup. In my other video, I explained where this came from, the x plus h minus f of x. I explained that h, what that stands for. Basically, it's just the difference in the distance or between x and x plus h. So we are now just essentially finding a limit as h approaches 0. And the reason that we're finding the limit as h approaches 0, from Desmos, I pulled up this function, which is just a parabola. And what I want to show you is that we are only given one point. We are given point 1, 1. And the point on the graph, as you can see, this tangent line, this tangent line touches. It just barely touches that point at 1, 1. So what we are really doing when we say that we want to know as we approach 0 for a particular point, what we are saying is if we were to magnify that point, we would end up finding that there are actually 2 points along that curve, and we're going to find the slope of the curve, or the slope at that point in the curve. And again, this would be magnified where the distance between these 2 points, the distance between those would be near 0. So that's what we're doing. We're finding an instantaneous velocity, or we're finding that exact slope at the point, at one point to the function's curve. So let's go ahead and work through this. There is a setup that I like to use, especially in the beginning as you're getting used to this. So there are 2 things that I usually write. I will write f. Let's see here. So I'm going to write f of x. And we already have it, but I just want to write this here so you can see what's going on. So we say that f of x is equal to x squared. Next, we're going to have f of x plus h. Well, what does that equal to? So in this function, we have, in the function f of x, we have 1x, and it is squared. So what we're going to do is we're going to insert this entire thing wherever x is represented in the original function. So in this case, there's just one. So we're going to put a parenthesis, open parenthesis. We're going to put x plus h, close parentheses, and it's going to be squared. So just like a composition of a function or of two functions, we're essentially just placing this x plus h into where x was. And now we have created both of the functions necessary to begin working through this derivative. So that's the first thing I do, and I'll continue to do that as I go through my examples. So let's go ahead and rewrite this as the limit of h approaches 0. And we're going to go ahead and replace this first position of the function of x plus h. We're going to replace it with what that's equal to. And we said it's equal to x plus h squared. So we're going to have x plus h squared. Next, we are going to subtract f of x. So f of x is simply our x squared. That's the entire function. So we just put the entire function in here, x squared. All of that is going to be over h. So at this point, I want to talk about why we are doing this, what we're supposed to look for as we're working through these derivatives. So if I were to plug h in using that direct substitution method, I would have division by 0. And when we set up these derivative equations, essentially what we want to do is look for a way to eliminate the problem with the denominator. The problem, obviously, is that we can't have division by h. So our goal or objective is to somehow reduce this in such a way that we no longer have h in the denominator. So let's continue. So now we're going to factor x plus h squared. So we will have the limit as h approaches 0, and we are going to end up with x squared plus 2xh plus h squared minus x squared divided by h. And something you're going to notice as you start working through these is that the first term is going to cancel out. Second, so the first thing is that your lead term will cancel. And typically it's going to cancel because that end term will create some type of equivalent but opposite value that's going to allow you to cancel that. And second, when you do this correctly, each term should contain an h in the numerator. So if you find yourself getting about halfway through and you've reduced and you find your numerator contains another variable, or you have a constant and each term does not contain an h, at least one h, you've done something wrong, because you won't be able to factor that h out, as we're going to do in this next step. So in this next step, we are going to say the limit of h as it approaches 0 for 2xh plus h squared over h. And as you can see, I have an h in each term. So I'm going to factor out an h from each term, which is going to give me, let me see here, scroll this down a little bit, which is going to give me the limit, and continue writing a limit as h approaches 0 until you use the direct substitution property, where you substitute that 0 in for h. So you have to continue writing what we were doing. So factoring that h out, I now have an h multiplied by 2x. That one's gone, so it's just going to be plus 1h here, divided by that h in the denominator, which I can finally reduce, which leaves me with 2x plus h. So at this point, what you can do is you'll be able to just simply substitute in the 0 wherever h is. And in this case, it's just going to be 2x plus 0. So we're going to end up with our derivative is going to end up being just 2 times x. And I did this a little different than the book because I want to show you that we just created an equation to find our tangent line to the curve. So this equation will give us that instantaneous velocity or the tangent line to the curve for any point that we choose. That way you don't have to do this each and every time for each individual point. You can solve this with your variables. So what they asked in the original question is, what is the slope at 0.11? And I think they're asking, what is the equation for the tangent line? So those are two different things. So we found our equation of we found the slope equation of the tangent line, which is different, is going to be 2 times x. So if I substitute in my x variable for the point, which is 1, I will end up with 2 times 1, which of course is not 2 times 2. So I end up with 2 times 1, which is just 2. Next, what we'll want to do is find that equation for the tangent line. So I'm going to write this in here. This gives you slope at any point using your x input. Then we're going to use point slope formula. And this is going to allow us to find the equation for the tangent line at a point. So the point 1, 1 is what we were looking for. So we have a point that was given. And we will just simply use our point slope formula. So it'd be y minus the y. So y minus 1 is equal to, we found that our slope in this case is 2, x minus 1. And that is exactly what I put in here, which is y minus 1 is equal to 2 times x minus 1. You could further simplify this to y minus 1 equals 2x minus 2, and it would give you the exact same tangent line, this tangent line that runs right through that point 1, 1. And that's exactly what we wanted. So hopefully this helps. And like I said, I'll do a few more examples, and then you can get to your homework. Thanks for watching.